My name is Jenny McElwain. I'm a PI in iCRAG 2, and I'm the challenge lead for the Earth System Change Challenge. So today we're going to have a short session, just 30 minutes. We have 3 speakers: Audrey Morley from University of Galway, Gordon Bromley, University of Galway, and Tomas Buitendijk from University College Dublin. And the first 2 talks are really addressing this concept of uncertainty in science. Now, I also like emojis, like our keynote speaker this morning. So if you look at the Oxford Dictionary for the word uncertainty, the definition, not able to be relied on, not known or definite. So uncertainty has a very negative connotation. But when you're looking at uncertainty in science, it isn't a negative. It's illustrating our limits of what is known, and it's a demonstration of what we don't know. So it's very powerful when you can constrain uncertainty or when you can map uncertainty in science. So looking at a definition of uncertainty in the scientific literature, it's defined as there is a range, or there's many definitions, many papers, but this is just one of them. There is a range of possible values within which the true value of a measurement lies. Now, if we look at this future projection of climate in Ireland, and this is from McElwain's Translate project, and it was heavily featured in the EPA, the Environmental Protection Agency's Ireland Climate Change Assessment Report. So this is a 4-volume document. And if we're trying to constrain uncertainty for our future climate in Ireland, we need to understand, where are we going to be? By the end of the century, are we going to be in the light yellow here, which is a 1 degree warming? Well, we're already there. Or are we going to be in the red, which is a 4 degree mean annual temperature range? And just in this one projection, there are 2 sources of uncertainty. The first is in relation to greenhouse gases. If we reduce greenhouse gas emissions quickly, we're on the yellow track. If we leave reducing greenhouse gases until 10 years, 20 years, 30 years, we're on the red track. So in a way, there's a huge involvement in public perception here, because these projections are based on our growth, our economy, our business, our politics, people. The other source of uncertainty in future climate projections, and this is any projection, is on what we call equilibrium climate sensitivity. So the forcer is greenhouse gases. It causes warming. If we have a low sensitivity model, this suggests a lower temperature increase to high CO2. A high sensitivity model is more warming in response to elevated CO2. How do we get this information? How do we work out how sensitive the Earth is to greenhouse gas going into the atmosphere from our energy use? Well, really, not everything, but so many of the projects we have in the Earth System Challenge theme, and the 2 projects that Audrey and Gordon are going to highlight today, is really, how do we constrain uncertainty? And it's in one component of the Earth system, and the Earth system is so complex. So the first talk is going to be on constraining uncertainty in the marine climate system, and that's Audrey. And then the second talk is on constraining uncertainty on land in the terrestrial climate system. And then the final talk in this session, we're going to move over to public perception of science, but I'll invite Audrey up here now to give her presentation.
Thank you, Jenny. I'm keen to talk to you about uncertainties. It's one of the key objectives of my research agenda. And the case study that I will present today is aiming at reducing uncertainties, especially in the polar and Arctic marine environments. And this is really important because at high latitudes, there are so many of the global tipping points that we are reaching in the near future. Why is the Arctic so important? Well, the Arctic is warming up to 3 times faster than the rest of the world. and the ocean is a key driver of that amplified warming or that Arctic amplification. And this has global implications because it impacts sea ice extent, ice sheet melting, primary productivity, permafrost melting, and so much more, which will impact these tipping points in the Arctic. Unfortunately, our observational and historical networks are very short and prevent us from defining the sensitivity of the Arctic to that amplified warming. In addition, we lack adequate paleoceanographic tools to look further back in time to define this Arctic amplification in the past. And this is what I want to talk about. These paleoceanographic tools is what we wanted to look at further. So specifically, I'm going to talk about the magnesium-calcium thermometry. It's these elements are measured in planktonic foraminifera, and I'm grateful that Chris actually showed a picture of these foraminifera in his talk earlier. They're teeny tiny marine plankton, and they live in the sea surface ocean. And the magnesium and calcium thermometry, as you can see in the top graph here, works really well in warm tropical and subtropical waters. And you can see here the list of subtropical and tropical species for which this relationship between magnesium, calcium, and temperature is very well defined. What you can also see, though, is that at low temperatures, and especially at temperatures in subpolar and polar oceans, this relationship or this sensitivity to temperature breaks down. There's clearly another component that is impacting the magnesium-calcium ratio. So our hypothesis was that besides temperature, there's a secondary control, namely that of seawater carbonate chemistry, that has a strong secondary control or sensitivity on that ratio. And our goal was to define that sensitivity and then mathematically isolate the temperature signature from the carbonate ion signature in the proxy so that we can resolve temperature in the past. So we did this, and we went out on many oceanographic cruises. This took many, many years. The data set I'm presenting to you is work that took at least 5 years, and we captured the living foraminifera and the water that foraminifera lived in to define that sensitivity to carbonate ion concentration that you can see here. We then used that regression and that relationship and applied it to the raw data set that you can see it up here to tease out or calculate out the true temperature signature that is recorded in the geochemical signature of magnesium calcium. So it works really well, and it works in the North Atlantic and in the South Atlantic. Any data set that we have applied it to, it works really well. But it also means that you will always need an independent proxy for carbonate ion concentration to resolve sea surface temperatures in the past. So you need, besides magnesium calcium, a second independent proxy. And we proposed that oxygen isotopes are a really good candidate for this particular species. I'm not saying it works for all planktonic foraminifera, but in this case it works. And the dependence of the oxygen isotopes on carbonate ion concentrations has been defined previously on planktonic foraminifera and other calcifying organisms, which would suggest that there's a universal control between the isotopic fractionation and carbonate ion concentration. Second, we demonstrated that the relationship between carbonate ion concentration and oxygen isotopes in this polar foraminifera is independent from temperature. And this is really important because that gives us the tool or the justification that we can apply this proxy in the past as that independent proxy to carbonate ion concentration. And when we integrate then the oxygen isotopes in our magnesium-calcium calibration scheme, we can then reduce sea surface temperature reconstructions to 1 degree. And this puts the polar and Arctic oceans on the same level now as the subtropical and tropical oceans in terms of reconstructing sea surface temperatures, which was not possible before. We then applied this correction scheme to several already published data sets. This is one of the great benefits of this tool. There are over 1,000 already published data sets of magnesium, calcium, and oxygen isotopes because the technology and the tool has been around for decades. So it gives us an opportunity to reanalyze and reassess all of these records that have been generated before. And we used it here in an application to calculate the temperature difference between the Holocene and the last glacial maximum, the LGM. And this is a really important calculation because that temperature difference is used to define climate sensitivity in model simulations. It is used to define the sensitivity also for future climate model simulations. And this is then really, really important because our data set shows that the amplitude of the cooling or of the climate response has been underestimated at subpolar latitudes around here. And again, this is really important because if we have underestimated the climate sensitivity, then we get into that red category that Jenny has introduced earlier. So these data sets, and there are many, many more, this is just one of the examples of what this tool can do, can then be used to redefine the sensitivity of the climate response and re-simulate polar amplified warming, cooling and warming, because it does go in both directions. And this is then really critical to look at how changes in the Atlantic meridional overturning circulations will affect ocean heat transport on any timescale, orbital, millennial, centennial, decadal, and so on. So with that, I thank you, and I will introduce my colleague, Gordon Bromley.
All right, good afternoon. On the surface, it might not be immediately clear how events that happened centuries, millennia, or even millions of years ago can help equip our society to face that most modern of challenges, and that is anthropogenic global warming. But it is only by assessing the full behavior of the climate system that we can really understand and say with minimal uncertainty, or the greatest certainty that we can, of what is the capacity of Earth's climate system for change. I think of this very much as reconstructing Earth's climate medical history, or its criminal record, depending on how you want to look at it. And one of the greatest, one of the richest and most nuanced troves of climatic information that we have available to us to do this is hidden on our landscape. It's right here. It's in Ireland. So today, I'm going to walk through how these data can be used to inform the future, or our projections of the future. And I'm going to use one example. This is the glacial vantage of a current paradox, an area, a knowledge gap, a place that we, Ireland's geoscientists, can minimize uncertainty. What am I pointing at? Okay, for the last 5,000 years or so, just like today, Ireland has experienced a strongly maritime climate. This is what we're used to, this is what we celebrate in culture, in the way our industry is formed, the way agriculture is set up. We expect minimal thermal variability throughout the year. That is to say, we don't expect hot summers, we don't expect cold winters. We expect year-round rainfall and windiness. And we complain about the weather. We complain about its unpredictability, when in reality, it is incredibly predictable, isn't it? This is the antithesis of extreme. But just underneath our feet, in a wide variety of geologic data sources, we find evidence that proves that this is not always the case. And I use the present tense there because this is the natural state of Ireland's climate. It is dynamic. All right, and so in these slides, you can see examples of ongoing projects. And this is a small selection of many projects going on based in this country that is using that archive of past climate variability and its impacts on our landscape to reconstruct what has happened in the past. Particularly, for me, areas of interest are these abrupt climate shifts, abrupt climate changes, because these are often used as analogs for future conditions, especially under global warming. And so we'll see one of those in a moment. But here, Lurs in the west of Ireland, Aeolian dust deposits. These are things that we normally associate with Central Europe or Eurasia. Evidence for permafrost, just meters underneath the fields that we are tilling for agriculture. Imagine that, permafrost here, with very abrupt onsets and terminations. Coastal evidence for perhaps important large-scale changes in atmospheric dynamics and windiness and so forth. And then, out of sight to most of us, is what lies beneath. Okay, and these potentially enormous troves of information on our hydroclimate and temperature and so forth. So these are just a few examples, and I haven't touched on any biological proxies whatsoever. These indicators of life that are screaming out that when climate changes, so does life. Life has to adapt. As humanity collectively adds about 40 billion tons of CO2 to the atmosphere every year, the question is, should we be preparing or thinking about abrupt climate shifts? And you might not use that term. You might use climate shock or just weird climate, and rapidly so. However you define it, should we be thinking about rapid change? And perhaps we should. There's a lot of uncertainty about this, I think, because we do not yet fully understand the mechanisms behind abrupt climate change, what causes it, what makes it propagate, and we don't understand exactly how it is manifested here on the ground where most of us live. And that uncertainty is important because, as previous speakers have mentioned, the data that we produce feed climate models. Now, these are frontline climate models which are projecting future scenarios as best they can. These are the models that are downscaled to provide regional or local simulations for sectors like agriculture, energy, insurance, health, you name it. There's a sector for it, and there could be a downscaled model output for that. The models inform directly the IPCC, which informs directly our national adaptation frameworks, our policies. And so, if there is uncertainty in any one of these, that is uncertainty in all of this. And as Jenny said at the beginning, we're trying to minimize the uncertainty there. You probably, I don't know if you can read these, but these are some of the experiments, the targets that are used. Paleoclimate targets that are used to calibrate these frontline climate models. They have to achieve this, they have to pass this test before they can be trusted with the future. We have the last interglacial, the last glacial maximum, deep, even I can't read that, deep time climates and deglaciation. If a model cannot meet these conditions, is it because we don't know the conditions or the model is not doing so well? All right, so the example I'm going to give here, it won't take very long. This is the kind of work that we're doing on the surface of Ireland, so terrestrial-based geologic reconstructions of past climate events and climate responses and information that is then being used to inform new climate models. This is the glacial vantage. And I did try to have a video in here, but that was beyond me. So we have a screenshot of it, worth finding on YouTube, though, if you can. This is a time lapse of the Mer de Glace, largest glacier in France. And many of us have probably visited it. And what you see over just years, like 2 decades, I think, maximum, you see this surface dropping. You see this ice mass, hemorrhaging mass, and just basically disappearing. And then you see it come back up again because it's a time lapse going round and round. The point is that ice, which is what I study, is merely frozen water. And it responds in a straightforward way to summertime temperature. So it's tracking the melt season intensity and or duration. And as it does so, it very conveniently leaves these landforms on the landscape. So these would be moraines, glacial boulders, and so forth. And these persist long after the glacier itself is gone. But what you see is a physical representation of climate. And so, this island has been occupied by ice many times over the last 2 million years. I'm sure it will be again. And we can quantify this, turn it into glacial data, into climate data. All right, it all starts with high-resolution mapping like this to reconstruct what was happening in the past. We can now apply tight chronology to this using surface exposure dating. It's a relatively new method, and just like radiocarbon dating last century, it is revolutionizing our ability to say what happened and when. So this project, you might see, is in the mountains around Kerry, Mayo, and Galway, and Wicklow. We are reconstructing glacial change during periods called stadials and non-stadials, or interstadials. Periods when it is thought that North Atlantic circulation weakened, and therefore our climate changed abruptly. What we don't know exactly is quite how, and was it seasonally uniform as a change? This is important, right? Because this is in the model calibrations. This was published today. Most of these data came out in geomorphology. Excuse me. This period in yellow you see here is called Heinrich Stadial 1. It's a good period to use as a model calibration target because the shit hit the fan climatically. All right? We see here Greenland temperatures, apparently very, very strong cooling. We see weakening of Atlantic overturning circulation. And what we see from a terrestrial vantage, based on our glacial reconstruction and the dates for that, we see the last Irish ice sheet disappear rapidly. That's what this peak is down here. It's all our dates from Connemara and a few from the Burren showing that this ice mass disappeared. And when I see ice disappearing, I think that's because it's getting warmer. That's the logical conclusion from that. Okay, so I see I'm pushing my time here a little bit. The take-home message from the land, from our glacial records so far, and this is preliminary, is that these periods traditionally associated with extreme cooling, anomalous cooling in Ireland and maritime Europe generally, are in fact characterized by anomalous seasonality. And that is to say that we go from mild summers and mild winters to something much more extreme, potentially very cold winters, but also potentially unusually warm summers. That is not something that is in our computer model targets, the calibration targets. And so without those, my question is, are those computer models really capable of projecting the future as accurately as we need them to? Seasonality, that is something, as I said, we don't really consider when projecting the future, but it looks from the geologic record like it plays a huge role in abrupt climate change, so we're working to constrain that. Thank you.
So my name is Tomas. I'm going to take us back a little bit to the question of uncertainty. So we're going to zoom out a little bit from sort of the scientific nitty-gritty, and we're going to move back towards the question of uncertainty and how to manage uncertainty in dialogue with public perception. So I think one of the questions that is faced by a lot of geoscientists, and I think scientists in general, is how do you communicate your science, and especially how do you communicate your science, how do you work with the public on the reception of science if there is a lot of uncertainty in your data, if there are scientific knowledge gaps, if you have to communicate some degree of uncertainty. So some of the research we do at iCRAG, and especially within the MESSAGE research group, which is an interdisciplinary research group working on coastal marine and energy research challenges, especially sort of emphasizing arts, humanities, and social science work, is working on public perception, on the communication and the dialogue around uncertainty. And I'm going to talk you through one project, which is funded by SFI and took place within iCRAG UCD, which is the Taking Stock project, and it focuses on public perceptions of marine sediment storing carbon. Now, just for a little bit of background information, marine sediments storing carbon are a significant source of blue carbon in the offshore environment. So they're a naturally occurring source of organic carbon that sort of accumulates over time on the seabed. And you can see this from the National Marine Planning Framework. There are potential hotspots. There's a lot of scientific uncertainty around where they are and how much carbon there is. But there are potential hotspots all around Ireland. And some of those are in very busy areas. So I'm particularly looking at number 2, if you can see that on the right. So that incorporates Dublin, but it also incorporates Dundalk Bay, a little bit further north, which is a busy area in terms of fishing, shipping, tourism, etc., plans for offshore renewable energy development. So you're introducing a new topic of uncertainty into an area where there's already an awful lot of human activity. And there are a lot of questions around these sediments. For instance, to what extent do they remineralize if they are disturbed, for instance, by bottom trawling or installing a wind turbine? Driving it to an extreme, and I don't think we quite get there, but driving it to an extreme, what if the question becomes, maybe you shouldn't put a wind turbine there because you disturb the seabed so much? Maybe that's not the case, but you get these questions around what can you and what can't you do, and how do you manage the public perception around that? And we decided to step into this process very early, while there is a lot of scientific uncertainty, to engage the public from the very get-go in the conversation on what do you think of these sediments and how should they be managed? Because in that way you can drive towards equitable and inclusive marine spatial planning, where community and stakeholder voices are heard from the beginning. So what did we do? We focused on Dundalk Bay, which in County Louth near the Northern Irish border. And we conducted a series of interviews and focus groups with people from the local community. And the approach we took was we built on the familiar to talk about the unfamiliar. So we built about what do you know about Dundalk Bay? How do you feel connected to Dundalk Bay? What does it mean to you? To then use that as a foundation to talk to people. What do you think of these sediments? Is it something you're concerned about? Have you ever heard about it? And how do you think they should be managed going forward? We used a really open approach, emphasis on scientific knowledge gaps. So we were very open about that. We said we don't have all the answers. And to avoid it turning into a Q&A with a marine geoscientist, the conversations were led by a non-expert, which is me. I don't have a geoscience background, which can be an obstacle, but in this case, I think it was a strength because it leads to a very level conversation. I'm not going to tell you you're wrong. I'm simply going to listen to what you think is going on. And that is a lot of what public perception is. Public perception can be entirely accurate of what people think is going on, say, on the seabed. It can also be inaccurate, but ultimately it is what people believe is going on that matters, and you need to have an understanding of that. So what did we find? Found a whole range of things, beginning with significant place meaning connected to the offshore environment. So there may be this assumption sometimes that out of sight, out of mind, the offshore environment is a non-place. That is not true, that's not the case. People around Dundalk Bay have a very strong connection to Dundalk Bay, cultural, economic, environmental, a long history of human activity in that area. And that also translated to experiential knowledge. People know what they're talking about. They know the bay. They know it either from a professional capacity, for instance, from working in fisheries or volunteering with the Coast Guard, or they know it simply from visiting the bay. Dundalk Bay is a very shallow bay, which is probably why it's so heavily sedimented as well. But people know the area. And in fact, the image you get here on the right, it's a bit of a hard and fast exercise, but what we did there was we transposed some data we got from participants on the left onto the map of Dundalk Bay about sediment types. And you actually find that on the right, that's the Infomar classification. The Infomar vessels don't run too deep to go all the way up to the coast, so you actually are able to fill in the white ribbon, what they call the white ribbon, a little bit. Now, is it 100% accurate? We would have to test that in a follow-up, but it does show that experiential knowledge to an extent. That being said, sediments are a new topic for research in the public. People are concerned about scientific knowledge gap. They want to be educated, and they think that the science should hurry up. Ultimately, they do want to be involved in decision-making. So whatever decisions are coming down the line, it is vital that local stakeholders and the communities have a say in that. Now, just to zoom out a little bit more from this, so why do we do this kind of research? It is in order to link geoscience policy and society, especially around, for instance, the management of uncertainty. So we would have gone to, that's the library event in Dundalk that we organized early last year. This is a photo from teaching at a secondary school, a site visit to Dundalk Bay with a secondary school that we did. And we also produced policy briefs to escalate that sort of knowledge and that input to a higher level. And all of that is to make sure that we create a stakeholder-inclusive process in managing natural environments that are meaningful to people, where people live, work, and that they have very strong connections to, in order to avoid a situation in which decisions are made without input from the people who actually live in those environments. I think I'm going to leave it at that. Thank you very much.
So just to wrap up this session, I hope with our speakers today we've demonstrated that there are ways of constraining scientific uncertainty, and it's hugely important because it has bearing on, for Ireland, how we're going to adapt, what mitigation strategies we have to put in place. So Audrey demonstrated through a biological proxy how she's been able to reduce the uncertainty of temperature estimates for marine systems. In Gordon's talk, he demonstrated that ice sheets are proxies for summer temperature on land, and by dating the sediment deposits from glacials, he can look at rate of change in response to a forcer, like a stadial climate change event in the past. And then Tomas has illustrated with his work with people in Dundalk Bay, and this was a quote from one of them: "It's critical that people feel part of any change that's going to happen." So storage of carbon in sediments is one way of, it's a solution, it's a mitigating solution for climate change. Technologically it may work, scientifically we may show that the carbon sink is big, but if public perception is negative, it's not going to work. So thank you very much for your attention.